In the previous lecture, we calculated what is the mean fractional energy gained by the particle when they are being scattered by the randomly moving scatterers. And we found out, so this mean fractional energy gain will be of the order of v by c whole square, where v is the velocity of the scatterer, and hence this particular acceleration mechanism is called as your second order Fermi acceleration mechanism. In this lecture, we will try to see what will be the accelerated electron distribution. By that, what I mean is, suppose I had the region of plasma where the mirrors are moving randomly. So for let us take t equal to 0, these mirrors are not moving. They are all, I'm going to keep everything as a stationary, and there's going to be an electron distribution, which is a monoenergetic. That's a very low monoenergetic. So monoenergetic one. So now at time equal to 0, I'm going to switch on the accelerators, and the scatterers are going to move. So eventually these particles are going to be scattered by these scatterers, and and after a long time, when the system reaches a steady state, we are going to see what will be we'll see the electron will form a distribution. So, and we want to calculate what that distribution is. But before we are going into derivation, we have to we will have certain assumptions, and this is because of the scattering, and the particle distribution is going to be homogeneous as well as isotropic. By that, what we mean, the distribution is going to be same in wherever region you are going to look, as well as it doesn't have any direction. So we are going to treat this. So what we wanted to find in this case is the evolution of the distribution function, momentum distribution function, that is f of p. So since I'm going to see the evolution of it, of course there will be a function of time also. I want to see the evolution of this momentum distribution function. So, and I have not used the momentum as a vector because, as I said, it's isotropic. It doesn't matter which direction you are seeing. So all we need is the magnitude of the p. So this will be the momentum distribution function. And if you are interested in the number density as a function of p, then your n of p dp can be written as 4 pi p square f of p dp. So we will use this later towards the end of it. So now what we are interested is the evolution of this momentum distribution function with respect to time. So that is del f by del t. So let me write it here. So what we are interested in is del f by del t, where f is a function of momentum and time. So without going into detail, each collision by the scatterer is going to impart some momentum to the particle. So there is going to be a diffusion in the momentum space. So this diffusion in the momentum space, we can write it as 1 pi p square del by del p into p square dp and del f by del p. I am not going into detail of how this term comes up because this all starts from your last law equations, and all we will not bother about it. So, and why this p square is coming is because we are using a spherical polar coordinates, because we need only the momentum magnitude. We don't need the px or py or pz. So we use spherical polar coordinates. That's why this p square term will come. So the interested readers, if you want to know how this term is coming up, you can look at the references given in the description. Fine. And this term describes the diffusion of the particle in the momentum space. So, and I want you to accept one more thing. So where your dp is the diffusion, momentum diffusion. dp can be approximated as dp p square divided by 3 tau and va by c whole square. Where so we will accept this term also. So for again, if you want to know how this term came up, you can have to go through the references given in the description, and then you will get it up. What it says is, suppose if we have the scatterers are moving at a velocity va is nothing but the Alban velocity. if the scatters are moving at the L1 speed, so and then the diffusion coefficient, the momentum diffusion coefficient dP will be approximately equal to P square VA by C square, and this tau is nothing but the mean scattering time. Fine. So we will use this equation. So let me write down this equation also here, some equations here. So this is going to be your dP, as the momentum diffusion coefficient, is approximately equal to P square divided by 3 tau VA by C whole square. Now let me keep adding the terms. So this is what is going to describe the diffusion in the momentum space, and then there's a source term, because initially there is the particle, and that particle is the source term which is going to feed in. As we started, as the scatter is moving, this particle is going to be getting energized. So this we will see it as, we will consider the monoenergetic, that is Q0 delta P minus delta function of P minus P0. What we mean is, before we start the accelerator, the electron distribution in the plasma is monoenergetic, and so the source term, the electron distribution which is going to be scattered off to the higher energy, that will be at a P0. So this is one, and we will have one more term. There will be loss term. So what the loss term is saying is that as the electrons are getting accelerated, there's always a probability the electrons will leave the system, will go away, they'll leave the system, and so that I describe as some escape time scale. So the time scale at which, the typical characteristic time scale at which the particle can leave the system. So, and that is a loss term, so that is going to be F divided by T, where T is the escape time scale. So this is I'm neglecting the radiative losses. So we can include the radiative losses, and the solution is going to be, so that will give a, what if you actually do it out, that will give me what is the maximum energy of the electron that can be accelerated, that is the radiative losses. To keep our description simple, I'm neglecting the radiative losses. Fine. So this is what we have to find a solution. So let us take this term. Let us have a careful look at this term. So what we are having is, so let me take this del by del P of P square dP del F by del P. I can write it as del by del P of P square dP into del F by del P plus P square dP del square F by del P square. So if you see this term, this is del F by del P. This gives a typically this is the acceleration term. It says how this distribution is going to change with momentum. So this is a term which is going to describe the acceleration of the charged particle, and this term, this is a del square F by del P square. It gives a dispersion. So this is the acceleration term with a dispersion term. So we'll keep it like this. So now, okay, fine. So then this is more, I want to equate it in terms of some acceleration. So I want to write this equation in terms of some typical acceleration time scale. So I'm going to define an acceleration time scale, TACC, based on this one. So what is going to be 1 by P cube into del by del P of P square dP. With this definition of this acceleration time scale, I want to express this equation in terms of my acceleration time scale. So basically, I want to eliminate the dP. So of course, I'm going to use this dP for this. When I substitute that, 1 by P cube del by del P of P power 4 by 3 tau VA by C whole square. So these are all constants. So this is going to become, so P cube gets cancelled. So it will become 4 by 3 tau into VA by C whole square. Great. So this is what we are going to, so this is what you go 4 by 3 tau VA by C square. So therefore, So, and so from here I can, so now, so from here I can always write, so 1 by 3 tau into VA by C whole square equal to 1 by 4 TACC. So therefore when I substitute it there, so my dP is going to become, dP will become 1 by 3 tau VA by C for better, therefore this is going to become P square divided by 4 TACC. So I can substitute this. So when I substitute this here, so what am I going to get is, so this will be P square by 4 TA, so this will become, so del by del P of P power 4 by 4 TACC del F by del P plus P square into P square by 4 TACC into del square F by del P square. Good. So this will give us, so this is going to become, so 4 gets cancelled off, so PQ by TACC into del F by del T plus P power 4 by 4 TACC del square F by del P. So let me substitute it in this equation. So the del F by del T is equal to, so this is going to be, we have 1 by P square here, so this is, let me take up this one first, so this is going to become P squared by 4 TACC del square F by del P square, and then again 1 by P square, so this is going to become plus P by TACC into del F by del P. Then the next of the terms, that is Q0 delta of P minus P0 minus F by T. Okay, so now we will try to find the steady state solution. That is, after a long duration, the spectrum is going to become, we are going to reach a steady state spectrum. We want to see that. To get a steady state spectrum, all we have to do is del F by del T goes to 0. So del F by del T go to 0, and then this del square F by del P square become dF square by dP square, because there's no more time, time is there. So and because F is going to be independent of time, so this becomes d square F by dP square. And then we want to look at the distribution which is greater than P0, because P0 is the injection energy, or P0. So we want to say distribution greater than P0, this will go off. So when I take P greater than P0, this term will go off. So finally, what we are going to have this equation is, under steady state, and for P greater than P0, this equation will become P square by 4 TACC d square F by dP square plus P by TACC dF by dP minus F by T, and this should be equal to 0 because that's a steady state. So this is the equation we have to solve. So let us do a bit more of So what we will do is, let us multiply by 4 TACC everywhere. So then this equation is going to become P square d square F by dP square. So this TACC cancels. So the 4P df by dp, and then this will become 4 TACC by T into F. That's equal to 0. So this quantity, what is the ratio between the two time scales? That is what? So this is a time scale. It is a particle being accelerated, and that's what we define the time scale from the momentum diffusion term. And this is the time scale, escape time scale, the time scale at which the particle is going to leave the system. So this ratio of these two time scales, let me write it as alpha. So then this equation is going to be p square d square f by dp square plus 4p df by dp minus 4 alpha f is equal to 0. So this is a Cauchy-Euler equation. So we can actually find a solution. We can solve this equation by using a substitution ln of p equal to z. So therefore p equal to e power z. So if ln of p equal to z, then I can always write dp by p is equal to dz. Fine. So then I can express all these terms. So first let me take p df by dp. P df by dp. So that can be written as p into dz by dp into d by dz. Correct? Yes. So dz by dp is equal to 1 by p. So this pp gets cancelled. So this is going to be d by dz. And let us go for this one. P square d square f by dp square. So this is going to be p square into d by dp of df by dp. And now let me use it again, the same one. P square into, so d by dp we can write like this. So that is dz by dp into d by dz of, again df by dp can be written as dz by dp into d by dz. So this is going to be p square. Dz by dp is 1 by p, and d by dz of, so this again dz by dp equal to 1 by p. So this is going to be 1 by p into d by dz. Now 1 by p is nothing but e power minus z. So this will become e power minus z. Fine. So this will become, and this is going to get cancelled, and we are going to get only 1p here. So let me open up this one. So this is going to be p into, first let me take this one. So that is p into e power minus z d square by dz square. Then this will be minus p into e power minus z d by dz. Okay. So yeah, so now e power minus z is nothing but 1 by p, so this cancels off, so, and this also goes cancels off, so this is going to be d square by dz square minus d by dz. Well, oh sorry, I have taken the f here, so this f is there everywhere. Yeah. So df is there, sorry. Oh, fine. So this equation will become p square divided by dp equals nothing but our d square f by dz square, d square f by dz square, and now we are having 4 times df by dz minus df by dz. So it makes plus 3 times df by dz minus 4 alpha f, that is equal to 0. And this is the equation we have to try to solve. And we will note down that how the relation between z and p, what we get is ln of p equal to z. That's the approximation we are using. Fine. So this is the equation we have to solve. So this, okay, let me remove this all. We don't need this one. Yeah, we had that term also. I will note it down. Alpha is equal to TACC by T. Fine. So we had d square. I can write it as an operator. So that is d square f plus 3 df minus 4 alpha f is equal to 0. So, or we can write it this operator in a quadratic form. So you all know how to do it out. D square plus 3d minus 4 alpha f is equal to 0. So this is a quadratic. So we can solve this as d is equal to minus 3 by 2 plus minus square root of 9 minus 16 alpha by 2. So if I take 1 minus 3 by 2 commonly outside, is going to become 1 minus plus root of 1 plus 16 by 9 alpha. Well, this I am going to call it as let us say chi. So we are going to have chi equal to minus 3 by 2 1 minus plus square root of 1 plus 16 by 9 alpha. So this is we call as a chi. So therefore d of f is equal to chi of f. So and d is equal to df by dz. If you remember what we have, d is equal to df by df is equal to dz. Dz is equal to chi of f. Okay, fine. So this will become, so when I take f here, df by f equal to dz, then we integrate back. What I am going to get is f. That is f df by f, when I integrate, is going to be log of f. So ln of f. Let me remove all these integral constants. We will not bother about it. So we will just get the shape of the spectrum. So ln of f will be approximately will go as chi of z when you integrate it. Correct? So now we know the z is nothing but ln of p. So therefore, f will go as p to the power of chi. Okay, so if I call this chi as a positive term, 3 by 2, then this is going to become minus. So minus. Let us take the minus here. So chi equal to 3 by 2 is 1. So f will be go as a p to the power of minus chi. And this is what it gives. Finally we got the answer. Our f of p, that is the momentum distribution function when this acceleration starts when it reaches a steady state, that will be a power law, and that goes as p to the power of minus chi, and chi is given by this equation. Well, and this is interesting to see. Now, if you see here, there are two options for chi. So only one thing will exist because other thing is unphysical. Let me explain why. So for example, let us take the Let us take the negative sign of it. So 1 minus root of 1. So this quantity is larger than 1, always greater than 1. So therefore 1 minus something greater than 1 is going to be negative. So this chi, if I take the minus term, the chi is going to be negative. When I put it back here, the power index is going to be minus minus plus, so it's going to be a positive index. So what it says is the dispersion, the moment of dispersion function. So that is related to my number. So that says as I go high in energy, as I go into higher momentum, the distribution function is going to increase. That means something diverging spectrum. That is what we are saying is this accelerator is something very unphysical that is going to accelerate more particle to the higher energy than the lower energy. This is an unphysical case because of course as the particle gains more and more energy, the chances of getting further accelerated are going to be less. So this is an unphysical solution. We need to have a minus sign. So we can, on that basis, we can remove this minus and we can always write it as a plus. So what we call typically is called as a diverging spectrum. So the spectrum cannot diverge because the system cannot dump more energy in the high energy part than the low energy. So this is not going to be one. So this is what your this is an interesting relation which gives us what is the shape of the electron distribution accelerated by the Fermi second order process or the stochastic acceleration process. When I plug it back there, so you can always find it out. So this is going to be, so you can always say your number density n of p will go as, that is p square f of p. So this is going to be p to the power of 2 minus chi. So this is what. So if I try to put it, so if you try to put this constant, what is 2 minus chi? What will be 3 by 2? When I put back there, 3 by 2 and this 2 minus, this will become 3 by 2 into 1 plus 16 by 9 alpha of 1 by 2, then I guess minus half. Correct. Yeah, I guess this is right. So now if I replace alpha, we know alpha is nothing but a TACC by TS, TACC by the escape time scale, acceleration time scale by escape. So therefore, this index, this is equal to 3 by 2 times 1 plus 16 by 9 TACC by T 1 by 2 minus half. So if I call it as S, then my n of p is going to be p to the power of minus s. And now this is an interesting quantity to see. So if you see how this power law, if we try to plot a power law in terms of ln of p in x-axis and ln of n in x-axis, this is going to be a straight line with the slope is your index s. Here it's minus s. Okay, so now, so if you see this quantity here, if as a t becomes larger and larger, that means my escape time scale is becoming larger and larger. That means the system is going to confine the particle more and more. The particle is not letting it to be escape from the system. In that case, t becomes larger and larger. So s decreases smaller and smaller. S decreases means becomes it's flatter, because if it's flat means 0, so it's going to become flatter and flatter. Okay, so now suppose by chance if you made this escape time scale to be much larger, so you confine the system, so you're not letting the particle to escape at all. That means this becomes infinity. So this goes to 0. So this becomes 1. So 3 by half minus half is going to be 1. So your S will be, in that case, at the t, as t tends to infinity, your n of p will go as p to the power of minus 1. This is the hardest spectrum one can get. So stochastic acceleration can actually produce a much harder. This is such a hard spectrum. So which is usually which is not usually people don't realize it, because people normally realize stochastic later on when we are going to see the first order acceleration mechanism, which is more efficient acceleration mechanism. So people think the first order mechanism can produce the harder spectrum. Harder spectrum is more in the high end, more high energy than the low energy. Okay, and whereas the stochastic acceleration or secondary acceleration produces steeper spectra. That's not fully correct, because if I have a larger region, if I'm trying to confine the particle as much as confine the particle, I'm not going to let the particle. And the stochastic spectrum can produce a much much flatter spectra than the one which can be created by the first order acceleration mechanism, which we'll discuss later. So, so this is what our yes. But one thing is, of course, since this energy gain, the fractional energy gain goes by V by C whole square, this is not an efficient accelerator. So the point is, it is not an efficient accelerator. So the particle will slowly build, the spectrum will slowly build. Whereas we will see it later in the first order acceleration or the other acceleration part. So the spectrum will build very fast. Only thing is, this will build slow, but it can produce a harder spectrum. Whereas the first order acceleration, it builds fast, but it can be steeper than your second order acceleration mechanism. So this is what. With this, we will see, this will stop the discussion on the second order acceleration mechanism or the stochastic acceleration mechanism. And next lecture, we will see something interesting. So that is the first order, or no, we will not before, that's the first order, but we will see something very interesting phenomena. What is that? So we are saying the plasma is flowing. So the magnetic scatterers in the plasma, they are going to scatter off the particle and they are going to get energized. Suppose if this plasma is having a shock front, that means there's a shock developed in the plasma, and we know, we have discussed earlier, a plasma is basically discontinuity between the two thermodynamic conditions. So the particle near the shock, they can get scattered off by this inhomogeneity, and they pass through the shock and reach other thermodynamic condition region, and again from there it can get scattered back and cross. So the particle is going to cross this shock due to scattering by those magnetic inhomogeneities on both the sides. So you will see this acceleration is going to be in first order in V by C, where we saw here first order, second order in V by C. This acceleration will be in first order in V by C, and this acceleration is called as the first order Fermi acceleration. This was found out later on, and this is the most efficient accelerator till now we know in the universe. We will see about these things in the upcoming lectures. Thank you.